which was the three particles, one, the Bogoliubov, and the vortex, the pi vortex with the Majorana fermion on it. And let me just rewrite the fusion rules for this one. And we derive this sort of hand-wavingly from microscopics. Etc. So notice that for each of these rules, the particle is its own antiparticle, because when I fuse the particle to itself, I always can go into the vacuum. Okay? So that was for C odd. And for C even, depending on whether you have C mod 4 equals to 2 or 0, which is basically just the only difference between them is what the pi vortex has, whether it has a half odd integer charge or an integer charge on it. You would get two sets of different rules. So A times A, there will be always 4 particles. Okay? And A times A bar is equal to the fermion. And from here on, you know how to get them. A times fermion is equal to A bar, etc. If I make a mistake from yesterday, just if I'm being dyslexic, correct me. And the other set of rules was A times A is equal to A bar times A bar is equal to psi, and A times A bar is equal to 1, and the same thing going A times psi is equal to A bar, etc. So the only difference between them is which one is its own antiparticle. In this case, one of them, A bar, and A is the antiparticle of A, and A bar is the antiparticle of A bar. In this case, they're actually opposite. A bar is the antiparticle of A. Okay? So let's first see. I don't want to go through. So I promised you that I'll show you that there's 4 theories here and 4 theories here, and I'll show you that. And there's 8 theories here. I won't be able, due to lack of time, to show you this, but I'll direct you where this is true, where you can easily see that, and I'll show you how to get it. Okay. So what I want to do now is the physical thing that I promised I would do, and take 2 C equals 1 superconductors, and kind of not look at their microscopics, but just look at this kind of axiomatic, low energy type of description of what vortices do when they come together, what they can do, right? This just tells you roughly, it doesn't give you any of the phases that happen in processes, but it tells you how things can combine. Okay? So I want to take 2 of these and get to an even C superconductor. Obviously, I know that I can do this in the bulk of the system. I can have models that can do this easily. So I should be able to do it at this axiomatic level too. I should be able to take, if this is some sort of any description of the theory that kind of strips down all the microscopics, I should be able to get from there to one of these cases by doing something. Okay? And the first thing that you see is that if I just don't do anything, these theories are very different. Okay? So 2C equals to 1. Let me just write down all the particle content in this theory. Okay? So I'm going to have 2 layers. So I'm going to call my particles like layer 1 and layer 2. Okay? So my particles are 1, 1, right? 1, there's 9 of them. I'm just going to write all of them. Can you guys see here? Okay. Where's the horizon? Is it? There's plenty? Okay. Okay, so I have 1, 1, 1 sigma, 1 psi. Then I have sigma 1 sigma 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 psi. And then I have in that, if I would take this basis, psi 1 psi sigma psi psi. All right, so first of all, I would have 9 particles if I just thought of them as being 2 layers, 2 decoupled layers. And I know that I've argued from microscopics that in both this case and this case I have 4 particles. Okay? So what do I do? Well, not only do I have 9 particles, but their fusions are completely different from here and here. Why? Well, let's look at the fusion of sigma sigma. You fuse them independently in each layer, and this gives you 1 1 plus psi 1 plus 1 psi plus sigma sigma. Does that sort of sorry, plus psi psi, what am I talking about? Dyslexia. Okay, does that make sense? Is it clear that that's what it gives? I can't tell if it's clear if I hear no, if there's no. Is it clear or not? Okay. No. So all you do is you just, this is, it's all the combination of sigma times sigma and sigma times sigma. But sigma times sigma can be 1 plus psi, and so can sigma times sigma, so you just take all those combinations, okay? And you get 4 of them, okay? All right, and obviously this is a highly non-abelian fusion rule. By non-abelian, I mean I get more than just 1 particle on the right-hand side, whereas in none of these cases do I get more than 1 particle on the right-hand side, okay? None of those 2 cases. So at the first step, you can say that there's nothing similar between 2 C equals 1 superconductors and a C equals to 2 superconductor. Yeah. Uncoupled. Right. But they're uncoupled. That's right. So you can either get the 2 in the upper layer can either be occupied or unoccupied, which is this. And the 2 in the lower layer can also be either occupied or unoccupied by a Bogoliubov quasi-particle. So that's exactly what this is saying. So, and as you said, the important thing is that this is kind of just 2 independent layers, right? So far I introduced no interactions. But now I can say, well, I'm just going to write down some interactions between layers. And the simplest interaction that I can write down, there's a lot of other interactions that could possibly be written down, but there might be other condensations available. But the one condensation that actually does the trick here is to look in the spectrum of this theory and see if there's something that you can condense, right? We all know that the simplest phase transition in physics is condensing bosons. So first thing that we're going to look is if there's somehow a boson in the spectrum of this theory that we can condense. And that would kind of physically mean that now I couple the layers and I add interactions between them and I kind of condense everything that I can in everything that could be condensed in these 2 layers. And what are the bosons in this theory? Is this a boson? It's a vacuum. It's 2 Bogoliubov vacuums. Yes, it's of course a boson. Now, this is not. This is a fermion because it's a boson. This is a fermion. This is not. They all have Majoranas. They're all vortices. Okay? I go all the way to here, and I find out that this is another boson because this is a fermion and this is a fermion. Right? So psi psi is a boson. And what I'm going to say now is that upon adding interactions, by the way, I don't know if anybody, maybe somebody knows if they can correct me, if anybody actually has a microscopic description of this phase transition where you just, you can realize this. I guess you can realize this as a more read state and then take two of them, but that requires an extra U1. I don't know if there's actually a microscopic description of this transition. Maybe there is. Maybe, does anybody know? Okay. So this is a boson, and what I'm going to say is that I'm going to condense it, by which I mean I'm going to make this boson be equivalent to the vacuum. Okay? So this is old theory. This is 2C equals 1. And now I add interactions. Okay? And make this boson condensed. So the new theory is going to have a set of particles which is the vacuum. Let's call the vacuum phi. I want to call the new vacuum phi just to differentiate it from this one. Okay? And what I'm going to do now is a map between the old particles of the particles of the old theory and the particles of the new theory, just by making an assumption that I can condense all the bosons that exist in the theory. Yes?
Did we know that psi had a spin 1 unit?
Yes. So I haven't. Yeah. So yeah. So we know that psi is a fermion, but basically we can also prove it. You can show from the if I solve the S matrix of this theory, the only S matrix compatible is from the S matrix you can get that psi is a fermion. You can't get theta of sigma. You can't get the topological spin of sigma from the S matrix, but from the S matrix you can get that psi is a fermion. The only compatible theories where psi is a fermion.
Psi has to be a fermion to make what you're saying possible.
It is, because it's a Bogoliubov quasi-particle.
But I want to make the following remark. I don't think one should describe what you're saying in terms of condensation, because I don't think a phase transition is involved. All you're saying is that because psi and the other psi are fermions, you can add to the Hamiltonian with a very small coefficient, an operator creates one and annihilates the other, or creates one and so it's really not a phase transition. It's an infinitesimal perturbation that goes to the situation you're studying.
There's not a phase transition, I agree. There's not a phase transition between two C equals 1 superconductor and C equals to 2 superconductor. Those are adiabatically continuable. So in that sense, there's no bulk phase transition. So I agree with your comment. But in the literature, this is called condensation. So I'm just.
Well, I discovered that in the literature, two types of things are called condensation. One, you can describe in a controlled way with an infinitesimal perturbation. That's what.
Right. Yeah.
Another isn't really under control. It requires a big change in the Hamiltonian, and it's very hard to be sure exactly what will happen.
So there is no phase transition. Let's make it clear. There is no bulk phase transition between these two. I'm just making a
Infinitesimal perturbation.
That's right. That's right. So, okay. So these two, so that's a good point. The two C equals 1 superconductors are adiabatically continuable to C equals to 2 superconductors. So in the bulk, there's no phase transition. But what I'm doing is I'm identifying this particle, which is a boson, with a new vacuum. So yeah, I'm introducing a small perturbation in the Hamiltonian. Okay, so the new vacuum is phi, and I have two bosons that I can identify with a vacuum. 1, 1, which was the vacuum in the old theory. So now I'm making a map between these particles in the vacuum, and psi psi, which I also identify with a vacuum. Okay? But what I know about the vacuum is that in any new theory, the vacuum, any particle times the vacuum, must give the same particle, right? If I just add the vacuum to the particle, if I fuse it, I get its own particle. So this is a new particle, the new vacuum. Okay? So if I want to make a map between the old particles of this old 2C equals to 1 layers of a superconductor in the new theory, I must identify every particle that fuses with a vacuum to the same particle. But now, since my vacuum in the old theory was this sort of non-trivial psi-psi particle, when this new vacuum fuses with a particle in the old theory, it can give me the same, it can give me two different results that now need to be identified. So let me just parse that statement. So what I know is that both of these particles go to the vacuum in the new theory. So this is old, this is new. So now let me make a simple example of this particle. What does this particle go into? Well, this particle, let's say 1 psi, goes into something that I'm going to call T4. Actually, call it T1. Okay, it's just one of these labels, T1. It's just a label. Okay? But I know that this 1 phi times that this T1 times the vacuum must give itself T1 in the new theory, right? Because this is just the vacuum. So, but now the vacuum in the old theory was 1, 1, okay? So obviously 1, 1 times 1 phi gives you 1 phi. But it was also psi, psi, okay? So in the old theory, so if I do this, psi, psi, and if I do this, 1 psi, and multiply them. But now look what happens. 1 times psi is equal to psi. Psi times psi is equal to 1. Okay? So now it means that I've got to identify with this new particle T1 both 1 psi and psi 1. Okay? Both of these are identified with the vacuum. So I'm just building a map between the old particle spectrum and the new particle spectrum. And this is how basically you're reducing the number of particles, because now your vacuum has two sets of fields from the original theory have condensed into the vacuum. This psi has condensed into the vacuum. You can add a boson term, okay? But since it was in the previous version, it was non-trivial. It had some non-trivial fusion, okay? Yes?
So basically you are saying that you are turning on interlayer interaction.
Adding, yeah, just add whatever Hamiltonian terms you want. All the possible symmetry allowed Hamiltonian terms you want. And we know that it's not actually, the statement is not entirely correct, but we know that most bosons can condense. There are actually uncondensable bosons, but I was planning to show some of that, but I'm not going to show it. Okay, but this boson can condense actually, so there's some bosons which can't condense. Yes?
What kind of particle is sigma sigma? You have a particle of sigma.
Sigma sigma is a vortex with the Majorana in the first layer and the vortex with the Majorana in the second layer. But we'll see what it goes into in the new theory. You can, could you say it louder?
Can I say that whether it's a boson or a fermion?
So it's neither a boson nor a fermion. It's this vortex with a Majorana zero mode in it. It's got different topological spins. Then it does different things under 2 pi rotations. Okay, just as we showed. So we did this experiment where I took 1 sigma and exchange it with another sigma in the previous lecture, and it gives you 2 pi c over 16 phase. Now, pure fermions wouldn't do that. Okay. All right. So this means that I have to identify these particles. So let me just rewrite this. So 1, 1 and psi psi both goes into the new vacuum. Psi 1 and 1 psi, because they differ by fusion with a vacuum, go into particle T1, okay? And now I'm going to do the same thing for everything else. So let's see what 1 sigma does. 1 sigma, if I multiply it with a vacuum, this is psi sigma, because this is 1 times psi psi, sigma times psi sigma, okay? So then 1 sigma and psi sigma must go into the same particle. They're identified, so call this T2, okay? Obviously, sigma 1 times psi psi which is part of the new vacuum, gives me sigma psi. So sigma 1 and sigma psi must go into the same particle, call it T3. Okay? And how many have I got left? So I've identified 1, 2, 3, 4, 5, 6, 7, 8. I've got 1 left, which is sigma sigma. Okay? So I want to know what sigma sigma does, but I'll reserve that for a little bit later. What I want to point out now is that I already have too many particles in the spectrum, even like this, even in the new theory. So I have phi, tau, T1, T2, T3, and whatever this will go into. Okay? This might go into more than 1 particle. So whatever that goes into, I already have too many particles in the theory to get the C equals to 2 system, because these are 4-particle theories. Okay? So there's something that's still amiss, and that's the concept of confinement. Okay, and basically what this roughly says is that even though I make a map from the first theory to the second theory by just using fusion with a vacuum, with a new vacuum, this map has to be consistent in terms of well, basically spins, but really what I mean is some sort of a topological spin, but let's think of it as just the spins. Okay, so what do I mean by it has to be consistent? Well, look at this particle and look at this particle. Whatever these particles do under 2 pi rotation, okay, if I map them into the same particle, there's a massive mismatch, and this mismatch has to do with the fact that this particle has an extra fermion, just a Bogoliubov quasi-particle, compared to this one. Okay? So in other words, if I rotate this one, okay, by 2 pi, I get a minus sign compared to if I rotate this one by 2 pi. Okay? So this particle is problematic, and this particle is also problematic. And the fact that you can't consistently define, again, I don't know of a microscopic way of doing it, but the fact that you consistently cannot define this map to have the same properties under, 2 pi rotation, just for example, spin rotation. One of them has an extra spin 1/2 with respect to the other one. Basically, this tells you that these particles cannot appear in the new spectrum of the theory. So these particles are what are called confined. Okay? So this is kind of a hand-wavy thing at the moment, and I don't actually know of a proof that if you just take out the confined particles of the theory, the new theory has closed fusion amongst itself, and I'll parse that statement soon. But the point is, there's clearly something that's amiss with these particles. They can't, I can't make a consistent map. So the conjecture is that in the new theory, they will not appear. So in other words, if I would create these particles as excitations in the new theory, they would kind of have an energy that grows linearly with the distance between them. So that grows the distance between them. So these particles are confined, and I kind of take them out of the spectrum by energetics. So that's kind of a conjecture that I think, somebody should microscopically give an example to, that if I create these particles in a microscopic model, if the map has a spin mismatch, because this obviously has a, upon 2 pi rotation has a mismatch, then those particles, if I build a microscopic model, have a linear energy cost, or have an energy cost to creating them free. Okay. So, but what does happen, however, and this is very important, is that so these are called confined particles. These are called unconfined. in all the theories that I've looked at, I don't really know a proof of this. In all the theories that I've looked at, the unconfined particles have their own fusion algebra, like this type of fusion algebra, and it's closed amongst the unconfined particles. You don't need to invoke confined particles, and that obviously should be the case. So in other words, two unconfined particles cannot, if I put A and B unconfined, on the right-hand side, I better not have any C that's confined if A and B are unconfined. And that's true of all the theories. Now, I don't know of a proof. Maybe somebody else knows of a proof of that, but I don't know a proof. Yes, sorry. You had a question? There was somebody in the back before. Okay. Sorry. Now? Okay. Yes.
Does this confinement have to do with the fact that when boson condenses, all the other particles that have non-trivial statistics with it, they sort of can't move around freely anymore?
That's right. I mean, that's the hand-waving argument. That's right. That's exactly. But I would like to actually see a microscopic model where I can do this, where that happens. And I don't know of any. Yes.
I'm a bit confused about your statement that 2 C equals 1 is adiabatically connected to C equals 2, because we stated before that C even makes
That what?
that the C even modulo 4 phases than C odd.
Right, so C equals 2, C equals to 1 is adiabatically continuable to C equals to 2 superconductor. So in other words, if I just take, I can take even a single particle, take 2 BDG Hamiltonians, each of them with C equals 1. Okay? Now couple them, right? So without, I can kind of, that's a C equals to 2 system, and I don't need to close any gap in that process. So that's all I'm saying. It's not adiabatically 2C equals 1. It's not adiabatically continuable to C equals to 4. But 4C equals 1 is adiabatically continuable to C equals to 4, etc. Does that answer your question? Okay. Yes? So T2 particles, so confined particles confined particle fusion can be an unconfined particle, right? Just they have a linear cost between them, but the crucial thing is that the unconfined particles form a fusion algebra by themselves. So in other words, if I have A and B unconfined, I can't get a confined particle on the right side. That's the crucial thing. And somehow, miraculously, in all the examples that we've checked, it works out, but I don't know of any proof just from simple arguments. Yes? Yes?
But when you say that 1, 1 and psi psi both are emitted by the vacuum, then it should occur at the same energy or at the same energy.
When I say what?
1, 1 and psi psi are your new vacuum.
Right.
And it should then be at the same energy.
Well, it's just like, for example, like all I'm saying is that, like say I have a Bogoliubov vacuum, like a superconductor, right? I take the 0 state, but then I hit it with, I hit it with C dagger, C dagger, C dagger of K, C dagger of minus K, plus some V of K's, right? So that's a condensation of those Bogoliubov pairs. So that's all I'm saying. What I'm saying is that the new vacuum is kind of a combination between these. Okay? The energetics is the energetics, that's based on a microscopic model that I don't know, but okay. Any other questions? Okay. So now I'm left with, so as was pointed out before, so these are confined, but I still have one left particle, which is sigma sigma. And I want to know what this sigma sigma does, right? And when I look at it here, sigma sigma has this type of fusion. But this type of fusion, I know now what the maps do to the new theory. This maps into the phi. This also maps into the phi. This maps into the T1. This also maps into the T1. Okay? So in other words, sigma times sigma in the new theory, sigma, sigma, let me just draw it here. So this goes into 2 phi plus 2 times T1. And this immediately tells you something very, almost tells you something very interesting. I would have to do more formalism to show you. But it immediately tells you that this sigma particle, okay, breaks into two different particles. So sigma, sigma breaks into, say, call it T3. I call it T2, T4 and T5. T4 plus T5, okay? And the reasons for that are manifold. I can't go through it explicitly, but you can kind of see here that you have something there's two particles on the right hand side, okay? So if I just had, for example, just one particle here, like T4, okay, I'll go through why it can't go into just one particle, but let's just assume it goes into two particles. It has also to do with the quantum dimension of this, which I haven't told yet. But let's assume first it goes into two particles, which it does. Then these two particles once I fuse them, okay, will give me T4 times T4 plus T4 times T5 plus T5 times T5. And there's a factor of 2 here because I'm assuming that fusion is commutative, okay? So now I have an identity between this side of the equation and this side of the equation, okay? And I have to choose what I'm going to equate. And what I'm going to choose, there's two options, obviously, that I can choose. First option is T4 times T4 is equal to T5 times T5 is equal to the identity field. And T4 times T5 is equal to T1. The second option is T4 times T4 is equal to T5 times T5 is equal to T1, and T4 times T5 is equal to phi. Okay? So there's only two options. Either T4 and T5 are their own antiparticle, or T4 is the antiparticle of T5. Okay? Clear? Yes?
What's the rationale for saying that sigma sigma has to split to
So you can write down, I kind of don't remember the simple rationale, but there's a very I can show you if I have time at the end. There's a very easy way of seeing that it has to go to two particles, okay? So basically the simple rationale is if you call sigma sigma, okay, going into n t times t, sum over t, okay, there's an equation that you can easily prove that tells you here that sum over all the particles t of nt squared is equal to 2. And there's only, if these are integers, there's only one solution, which is 1, 1. I think there's actually a simpler argument.
The simple argument would be since phi is the identity, any particle has to have a single fusion channel with the identity. The prefactor of the identity has to be 1. That's the maximum of.
Okay, yeah, but okay. Okay, so what? Which one? This.
The multiplication on the left, you take two particles.
Yeah.
And the sum on the right is sum of all kind of species that could be there. But from this point of view, it's not clear what the 2 means.
Oh, what? So what my 2 means is. So. That's right. So these. Yeah. Under condensation, I did, right? Because I got 1, 1 plus psi, psi. Well, I have to identify them because it's identified with the vacuum.
What does that mean that there is a 2 there?
Well, you know, basically, I mean, this is again, you know, why, you know, because 1 plus 1 is 2. But I understand your concern. This is a bit hand waving. If I wanted to actually get these n factors, what I would write down is that particle A goes into a sum of these particles t, and these would become my fundamental whatever splitting coefficients. Okay, these are the same things that you know, that these are the same things that in chiral extensions of algebras, you get the matrices that commute with the S matrix, and these, you know, you get them. The matrices that commute with the S matrix are n transpose. Okay, these. Once you get, this is just a hand-waving way of basically doing commutativity or associativity of this following fusion diagram. A times B goes into NAT, T, NBT, NBS, S, but they also go into some NABC, C, which goes into some NABC, NC, R, R. And now you say that, you know, to make a consistent theory, you make this diagram associative. Okay, so you say that these two are equal. This is just a hand-waving rewriting of this. This will tell you, there's a following constraint that you can get from this. It will tell you that the fusion coefficients of the new theory are ST, NRA, NAR, NBS is equal to the fusion coefficients of the old theory times this, times the splitting coefficients. So I'm just doing a hand-waving way of actually obtaining. What you want to obtain is the fusion coefficients of the new theory and the splitting coefficients in terms of the old fusion coefficients of the old theory. And the only input that I'm actually using here is that this is associative. And I've used it a couple of times here without actually mentioning it. I've used it. Okay? So what I'm saying is I split the particle, but now I'm making all the splitting consistent with fusion of the old theory and the new theory. Okay? And that's just kind of a hand-waving way of So what this 2 means is that one second. What this 2 means is that n sigma sigma, this A and B are sigma sigma particles. Okay? I mean, I won't get to like even half of what I have to do, okay? Sigma, sigma particles, sigma, sigma particles, okay? 2C NCR, okay? Sum over C times the particle R here, okay? This particle R is in the new theory, okay? This particle R is phi and T1. Okay? In this case. What I mean is that this coefficient is 2. This number is 2. And that's just because if I sum this with this, sigma sigma times sigma sigma has n 1 1 sigma 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 is equal to 1. It also has n psi psi, sigma sigma, sigma sigma is equal to 1. Okay? Just from the old theory, right? Both of these are equal to 1. Now, they're both identified in the new theory, so this number is 2. If I pick C to be 1 psi and psi 1, which are identified in the new theory, then this number would also be equal to 2. These two just tell you these numbers. Okay? Does that answer your question mathematically at least? Okay. Okay. So, you notice here that I now have both fusion rules for the C equals even case. Yes? No. Yeah, but one psi and psi 1 are they're both T1. So in the new theory, right? In the new theory, this is identified with a vacuum. This is identified with a vacuum. This is identified with T1, but this differs from this just by a psi-psi boson. What do you mean, how they? So think of this as two vortices in the upper layer and the lower layer, independent. Right? I take two vortices in the upper layer, they can give me either 1 or psi. I take two vortices in the lower layer, they can also give me either 1 or psi. Okay, now there's four possibilities. And those are the 4. Maybe I'm not understanding your question. Is that? I'm saying these are the possibilities of fusion when you fuse, which one you get. It will depend on how you initialize your state, but the microscopics of it, I could basically pick one of these if I wanted to through energetics by just, adding some capacitance next to these. But the point is, there's 4 options. Is that clear? That maybe I'm not understanding the question. What is it clear that there's 4 options? Because if I have 2 vortices that I can fuse in the upper layer and 2 that I can fuse in the lower layer, these 2 can be either occupied or unoccupied. These 2 also can be 1 or psi, occupied or unoccupied. So I get 4 options.
So it's not simply like plugging I sum over each component of the
If you agree with this, so if we understand this, which is, then so what's, can you rephrase your question? I just don't understand what the.
My point is that you can simply sum over each vector with respect to each component. Then you can 2 plus 2 psi, 2 plus 2 psi for each component. So we have this kind of operation for this vector right now.
So it's not a vector space.
Oh, it's not.
I can sum over each component. Just think of it physically. I don't understand with summing over each component, but think of it physically. You're just taking vortices and coupling them and either occupying, you look at the possibilities of either occupying them or unoccupying them. Okay. There's no phase transition in the bulk. Okay, the bulk of the C equals. So yes, so I can do it by just a small deformation of the Hamilton. Well, I mean, depends what you, okay, I mean, depends. So the energetics of it is, I don't want to get into the energetics of it just because I don't, probably I don't understand it. But so this is just an argument that doesn't have to do with energies, okay? It's just an argument that basically tells you that if I have different spins, then I can't basically make a consistent. If the two different spin particles map into the same particle, I can't make a consistent, I can't make a consistent mapping, okay? So the one way to understand that is that you would have these particles confined. Now, of course, I understand your worry, but we're talking about different energy scales. The point is there's no phase transition in the bulk between these two, and that's true. Now, how the energetics works, let's not figure this out now because I don't know it. Okay, I don't actually think anybody has produced a Hamiltonian that has this, an electronic Hamiltonian, microscopic Hamiltonian that has this. Okay, so what I want to point out is that you get here both fusion rules that you would get in the C equals to 2 mod 4 and C equals, so this is C mod 4 is equal to 2 or 0. You get both of these fusion rules there. So what's the problem? Because only one of those has to be correct. So only one of those fusion rules has to be correct because I took two C equals 1 superconductors, put them together. You can call this T4 and T5 A and A bar, right? So I can call T4 A and T5 A bar. And then I get exactly those fusion rules. But you can see that I get not only the fusion rules for 2, I get the fusion rules for 4. And at this level of sophistication, you cannot distinguish between them. Okay? So you would say something is wrong. So at this, there's nothing else if I just use the fusion and the condensation, so the identification of a boson with a vacuum, that can distinguish me between these two rules. Okay? They're both valid. But I know that since I put only two superconductors together, two C equals 1 superconductors together, I cannot get to a C equals 4 superconductor. Okay? So I must get to C equals to 2. So what's the problem with that? Well, the problem with that is an extra input. If I know the topological spin of the, say, T4 particle, so if I know the spin of the T4 particle, so this T4 particle came from sigma sigma, okay? Now, as I argued through this vortex kind of exchange, the spin, the phase, the equivalent of the spin for a sigma particle is e to the I 2 pi over 16, okay? Because for C equals 1, there was a C here. So this one is this to the second power for sigma sigma. So it's e to the I 2 pi over 8. Okay? And that's also the topological spin of the T4 particle. Okay? So the mapping is consistent in all the spins except for the confined particles. The confined particles have this issue, this problem. But the map is consistent for the other ones. You see, this is a fermion, this is a fermion. And T4 and T5, since they come out of sigma, they have the same spin, which is this one. Okay? Well, if you add more input to the problem, you will find out that depending on whether that for this particular value of the spin, only one of these rules gives you a consistent theory. Okay? So in other words, if I actually took this fusion rules and tried to build a theory that's consistent with this topological spin, I would only be able to do it with one of the fusion rules. Okay? And that's actually how you basically get to the C is equal to 2 theory. you basically kill one of these fusion rules because it doesn't fit well with the topological spin. And that you can do just from the S matrix. So how much time do I have since I wanted to do the...
Well, you have until about 11.
Okay. Okay, so let's sort of very fast understand how to actually get that only one of these theories is valid and is the correct one. And for that, I need to introduce a bunch of things, and I don't know if I actually have enough time, but I'll try. So, okay, there's another hand-waving way that you can do it, is by just going back to C equals 2 mod 4 and C equals 0 mod 4, and just computing, exchange of vortices. And then you'll see that the phase that you get for the exchange of vortices is for the particle, T4 or A is e to the I 2 pi over 8. Okay? So, and if you do the same in C equals 0 mod 4 theory, if you do the same in C equals 0 mod 4, you won't get that topological, that number for the exchange of two vortices. So you won't get this phase. So that's how you can pin out which one of these theories is correct. But basically, just at the level of condensation, just from the fusion rules, you can't say which one, whether 2C equals 1 superconductors gives you a C equals 0 or a C equals 4. You need to introduce extra information and compute the phases of these vortices. Okay. But let me show you how to do this in general, just by having some fusion algebra, and then obtaining the S matrix and obtaining all these topological spins in general, at least for these two theories that I've done here. Okay, so to do this, I'm going to need to go a little bit fast. So what we're going to do is we're going to use this pictorial representation or diagrammatic representation of braiding processes that happen in these theories, okay? So what we're going to say is that this is the time arrow, and a particle moving forward in time, particle A, we're going to call it by, an A line with an arrow. Now, of course, this is equivalent with an antiparticle, A tilde, so A times A tilde, moving in the opposite direction. Why? Because, well, if I just do this process, okay, with both A and A, not A and A, A and A bar, if I do this process, then obviously A can annihilate with A bar, and I get here the vacuum, okay? And I can just pictorially delete a vacuum line and represent it by a particle. So a particle A is equivalent to its antiparticle going back in time, okay? Just because I can kind of annihilate them at some point in time or create them out of the vacuum if they're antiparticles, okay? Now, I require a kind of a leap of faith and basically require to think of states in this Hilbert space as some sort of configurations of particles with lines in the past and lines in the future. So the states, we define, so all that we're computing here, there's no Hamiltonian, the Hamiltonian is 0, all they're computing is amplitudes, okay, of processes, like braiding or phases, okay? So states are things that have particles in the future, so call these A, B, C, okay? And these particles do something. There's a big black box here. And come out of particles in the past, or call it E, F, G, okay? Now, it doesn't matter what happens in this box, but most of the things that will happen in this box are going to be braids, right? So what I'm trying to look at is to look at how states change as I take, one vortex around another, or by exchanges or braids or whatever you want to. Okay, so it doesn't matter what happens in this black box, but some of the things that can happen, as I said, are braids, exchanges, or even more complicated knots, whatever, etc. They're mostly just all decomposable in exchanges. Now, what I want to say is that the game you're going to play is that whatever happens in this box is equivalent to whatever happens in any other box, as long as the ends are staying the same, are staying where they are, okay? So if the ends are staying where they are, and I haven't cut any word lines in this box. So in other words, what I can do in this box, I can, if I have two things that do this, this is in this box, this is equivalent to, for example, if I have things doing this, okay? So, because as long as I keep the ends fixed, this is all that matters. Okay. So basically, everything that you can do with a piece of string that you've got around, like your badge, that doesn't require cutting the string, is allowed. So topologically, this is equivalent. Why? Because this would actually just mean, say I just take a vortex here. I take two vortices, and I take another vortex, and do something like this, okay? If I do something like this, take a path and move it like this, then nothing really happens, okay? Well, it would be kind of equivalent to this. This is moving up in time, okay? But if I do something like this, sorry. But if I do something like this, okay, now that's a non-trivial process, because what I've done now is if I keep the ends fixed, I've had to have cut the wire, okay? If I don't keep the ends fixed, I can do this process and move it around, but if I keep the ends of the particles fixed, this is a process that has done this. Okay? So I can't get from here to here without cutting one of the wires, which I'm not allowed to do. So these two are not equivalent, but this is equivalent to this. So that's the name of the game that you're going to play.
So just to be clear,
Yeah.
the set of states is the collection of all processes?
That's right. So there's states and there's amplitudes. States have end particles which are free, okay? And they're indexed by, the end particles and the beginning particles, okay?
And
Now,
fixed source and target, you get a Hilbert space of possible states.
that's right.
But if I look at all of them together, it's not a Hilbert space, or do I take the direct sum?
You take the direct, yeah. So you take, so I'm just getting to this. You can just build everything out of products of fusion and splitting Hilbert spaces and operations such as exchanges of things. Okay. So let's define two fundamental Hilbert spaces, and this is the splitting, where particle C splits in particle A and B. Okay, and here I'm going to have an index mu, which goes between 1 and the number of ways that this particle can split. So remember, I had A and B goes into sum over C, and A, B, C, C. This is just telling you the number of ways that particle C can split in particle A and B. So I'm going to identify this with a ket, say A, B going to C in, there's more than one state, and that's indexed by mu. Okay? Alternatively, so this is called VCAB. It's a splitting space. So now I'm going to define like a fusion space in which particle A and B, when I don't draw lines, just the arrows, just assume them all up. Okay? This is VAB, goes into C. Okay? And here I'm going to have this state belonging to this space. Okay? And then, actually, let's do this. And then the next thing I'm going to define is completeness. Okay? So completeness diagrammatically, and diagrammatics is kind of very useful in this field because it actually allows you to prove a lot of things without a lot of math. So completeness just tells you that sum over C of this is equal to 1, sum over C and mu. Okay? Which is just A, B, C mu, C mu, A, B, sum over C. Okay? So in other words, if I had a sigma sigma here, how many C's would I have to sum over? 1 m psi. Okay? And normally there's a norm here that people use that I'm not going to get into the details of which, so I'll just call it n. This norm is actually dependent on A, B, and C. You'll see it in the literature, but I don't want to go through it. Okay. The other thing that I'm going to use is orthonormality. Which just diagrammatically means that this diagram is diagonal in the C and C prime particles. And it's obviously diagonal up to a norm. So now this is norm times the same norm that you've got there, delta, which I don't want to write down, delta mu mu, delta C C prime. Okay? This norm is, of course, the quantum dimension of the particle, by which we'll go through now. Okay, so these are the only things that I need. And by using this, by using this and these coefficients, so the input of a theory are going to be these coefficients, which are non-negative. And now we're going to try to build a consistent theory out of this. Okay? And again, the consistent theory, just the only inputs are the fact that whatever you can do inside with these world lines, all you can't do is cut things. Okay? Anything else is allowed. So these are states, but following things are amplitudes. So this, for example, is an amplitude. It means I create a particle A and its antiparticle out of the vacuum. I propagate it in time. Okay? And I annihilate it also in the vacuum. So in other words, for all these states, I can apply a projector here, which annihilates to the vacuum. Sometimes it's going to give me 0 if A and B don't have a fusion channel into the vacuum. So for example, if A and B is psi and sigma, psi times sigma is sigma. If I try to project it to the vacuum, it's going to give me 0. But sometimes it's not going to give me 0, such as if I had sigma sigma. In particular, any time that you have a particle and its antiparticle, it's never going to give you just 0, right? Because antiparticle, you always have a fusion channel to the vacuum. So this diagram is, of course, that norm, okay? But I don't want to call it that norm. Let's call it dA for reasons that we'll soon understand. It's the quantum dimension. So now I want to obtain dA in terms of these just n's. And this is kind of like in most books. What you do is you take two diagrams. Well, let's just take two. Take two separate particles, A and B. It's in most books, but it's incorrect in most books, actually. So you take A and B, you shrink what you can, I can always, shrink this and kind of like move it inside of A. So this is identical to this, for example. Now what I do is I just focus on this part of the diagram, and I have A and B, okay? And I use my completeness relation. So this is a completeness relation. So if I wasn't looking here, this is just A and B. This is equivalent to this, okay? Sorry, what?
How can you get from the two loops to the one on the right without cutting?
Right. So you don't cut, you just go underneath it. Okay? What I can't do is so this is allowed, remember? So what I said, yeah, so you just slide it. So this is allowed. So now I just can, right? What is not allowed is this, because that would mean cutting it. I wouldn't be able to get from here to here. Okay, good. So I just slide it underneath. Okay? So this is, the amplitude of this is dA times dB. But I now insert a full set of states here. So this is just sum over C and mu of, this is B, this is now C, this is A, and this is mu at each. So this mu runs from 1, that mu runs from 1 to n A, B, C. Okay? But now if you have this, you can just take it around like this. You can just take these endpoints, move them here. This is just sum over C and mu of C mu A, B, okay, mu C. And there's a norm that I forgot, but the only reason why I forgot it, and I'm going to forget about norms, is that whenever I use this relation, the completeness relation, I'm then going to use the orthonormality relation. So this norm will vanish when multiplied by that norm, because this comes as 1 over m, that comes as n. Okay? So they'll just vanish. So I just got rid of this norm, for sakeness of presentation. Okay? So now I'm going to use the orthonormality relation. So this is just sum over C. I have a delta mu mu here. Okay? I can close this with a C here. This is C. But the sum over mu is going to give me a number. Okay? And that number is n A, B, C. Right? Because mu runs from 1 to n, A, B, C. So what I've just proved is that dA times dB is equal to sum over C n A, B, C times this diagram. But what is this diagram? It's just DC. Okay? So now this is kind of a very important equation, because it immediately tells you that if I look at these matrices N, A, B, C, and write them down as a matrix N, A, B, C, as I wrote them down at the beginning, right? I said that these are mutually self-commuting matrices. Then D, C, this vector, has got all the components, D vacuum all the way to D last particle, is an eigenvector of all the matrices, right? So we knew that the matrices have common eigenvectors, but this is an eigenvector of NA, okay, with eigenvalue dA. Okay? So now why is that important? Well, there's a commonly cited result in the literature that invokes the Frobenius-Perron theorem. So basically so notice that this matrix has non-negative integers. non-negative numbers as entries, and they're also integers, but that's not massively important, just that they're non-negative. And there's a strong version of the Frobenius-Perron theorem which tells you that if that matrix was positive, so if it didn't have any zero entries, then there would be a highest eigenvector with non-negative entries, and the eigenvalue of that highest eigenvector would be the largest eigenvalue of this matrix. Okay? So that actually would be very beneficial to us because we know that this eigenvector has non-negative entries, this D1. Okay, so then we would know that dA is the largest eigenvalue of NA. Okay? Now, that result is quoted in all literature, but it's actually not entirely correct because this matrix has non-negative entries, not just positive. And I can't go through it now, but I can refer you to some notes that I have with Titus Neupert that basically give the proof that that's the largest eigenvalue. So you can still use the weak, it's called the weak version of the Frobenius-Perron theorem, where these are just non-negative, okay? So they allow zeros. But if you know that this eigenvector is all positive in the sense that it doesn't have any zeros in it, which it doesn't, all these d's are just amplitudes of the vacuum, so they can't be zero. So if you know that this is a positive vector, that you can still prove the strong version of the Frobenius-Perron that this is the largest eigenvalue of NA. So this d is the quantum dimension. Well, it's the largest eigenvalue of NA, also known as quantum dimension. Okay? And why is that important? Well, the reason why that's important is that this governs the growth of the Hilbert space of the state of the fusion channel. So if I take A times A times A times A, the largest number here is going to be dA to the number of A's. So say I have a number of A's, number of A's. Can anybody tell me what dA is for the sigma particle since the Majorana? So two Majoranas form a complex fermion, which can be either occupied or unoccupied. Square root of 2. Okay. All right. Now what I want to show is well, not that I want to show, but I want to, due to lack of time, I won't be able to do the braiding, but I'll be able to do the S matrix. So one fundamental quantity that we have in this field is the amplitude of a particle going around another particle. So that's not just exchange, that's full braiding. Okay? And pictorially, I can represent this as this. Okay? Call it BA. Okay? And generically, there's a normalization factor, which is called the total quantum dimension, which is made to make this matrix unitary. Otherwise, it would be just, d squared times s dagger would be d squared times the identity matrix. And this is just square root of sum over a dA squared. Okay? All right. So what I want to prove without introducing, actually let me see if I can, without introducing, I think I can, without introducing braiding, I want to prove the Verlinde formula for this, and then refer you to how to get these S matrices. So without introducing braiding, I want to show you that there's a relationship between this amplitude which just takes, without introducing, exchange, the R matrix. This is braiding. I've just taken one particle, B, and taken it around A. And this is a number, okay, that I'm going to get. And this matrix is unitary, which I haven't proved to you, but I can prove. Well, one can prove, okay? So I want to show you that there's a relation between this S matrix and these fusion coefficients, okay? And the simplest way of showing you is the following. First, I want to compute what this diagram is, okay? So this diagram, since I have only one, so if I didn't look here, okay, I have the X particle coming in, the X particle coming out. So this has to be some number, or some phase, actually it's a number, times the particle X, right? Because if it was two particles, they could be in a different fusion channel here, they could be in a different fusion channel there, but if it's just one particle, this is my only option, okay? This can do things in here, so it could do things in here like, okay? But all these things are removable by operations that I haven't told you about. They're just, all those, those are just twists. Okay, so what is this number that I want to find out? Well, this number is, the way I find it out is I project this diagram. So what I do is I take this and add, so I take this diagram and add an X line, okay? Or X tilde, really. So this is equal to alpha times this, okay? But this is SAX times the quantum dimension, okay? Which is equal to times the total quantum dimension D. This, what is this X? Well, this X I can also interpret it as a vacuum, and X, this is equal to X, okay? Because the vacuum doesn't braid, doesn't do anything non-trivial. So this is S1X times the total quantum dimension. So alpha is SAX over S1X, okay? That's this number. And of course, can anybody tell me what S1X is? So this is S1X, this is S1X times D, but what is this? dx. So the first column and row, because the S matrix is symmetric, of the S matrix are just the quantum dimensions, okay? All right. So now what we're going to do is we're going to look at so that's the first process that I'm going to look at. Now what I want to do is look at the second process, where I take two of these, okay? And that's kind of a normal thing that you always do in this diagrammatic expansion. You kind of find something that projects on one particle, then find something that projects on two particles. Okay? So I want to look at what this does, X, A, and B, this process. Now, I can think of it as a separate process where I have S, this is X. So this is a product of this process times this process. So this is SAX over S1X times SBX over S1X. That's one way I can think of it. Times X, of course. Okay, because again, if I looked here, there's nothing coming in and out but X, so this has to be proportional to X. But this is also, I can kind of just slide this without cutting anything underneath here. So this is also the same thing as this. Okay? Where I've just kind of taken this world line well, and slide it underneath this one, okay? I haven't cut anything, so every intersection is still the same as before. Is that clear? Does that make sense? Okay. So now what I'm going to do with this is I'm going to introduce my beloved completeness relation here. Okay? So what I'm going to do with this is do this. Introduce it here. Okay? A, B, mu, C, A, B, A, and this is sum over C and mu. And there's a normalization factor that I'm going to get rid of when I use my orthonormality relation. So I'm not going to put that in. Okay? I can, I'll, in the notes that's put in, but it's cumbersome and you don't need it. So now what you're going to do is extend this C line particle and take it around, again, without actually without cutting any wires. You can just play around with it. Just make wires and play, or strings and play around with it. So I'm going to take this ends here. So this is identical, sum over C mu of this. This is B, this is A, this is X. Okay? But now I'm going to use my orthonormality relation. This is sum over C and sum over mu of delta C. There's the same C, so the delta C is done. But the delta mu, okay, mu prime, mu and mu prime are the same. So this is also taken into account, times C and X. Okay? Now, I have this factor of mu. How many mu's are there here? Well, the mu's just index the number of possible splittings of C into A and B. So mu goes from 1 to n A, B, C. So I can take the summation over mu and just add n A, B, C. Okay? But this is obviously sum over C n A, B, C, S, C, X over S1X. Okay? So I'm going to take 5 more minutes than if that's okay, just to have. Is it okay? 5 more minutes? Okay.
Keep it strictly 5 minutes, though, because we have a
Yes.
short break before
Yeah. It'll be only 5 minutes. Okay, so what we've proved is that SAX over S1X times SBX over S1X is equal to sum over C NABC SCX over S1X. Okay? So this is called Verlinde formula. And what it tells you is something very remarkable. It tells you that the S matrix are the eigenvectors and the eigenvalues of the fusion coefficients. Okay? So it tells you that n, if I was to write this as a matrix, NABC, sum over C, SCX over S1X, is equal to eigenvalue is SAX over S1X times SBX over S1X. Okay? So once you have once you have the fusion coefficients, you can get the S matrix by just diagonalizing the fusion coefficients. Now, there's an issue of whether the S matrix is invertible or not, and that basically defines unitary, modular, tensor categories or not. But for all the stuff that we've assumed so far, it is. Okay, so now what I want to do is I can't go into braiding, so I'm only going to be able to show you that I can't go into exchange. I've kind of done braiding, but I can't go into exchange. So what I want to show you is that there's, I can't show you that there's 4 theories for each of the fusion rules, but I can show you that there's at least 2. Each of those 2 break down into other 2 when you look at exchanges. So this doesn't know about exchange yet, right? This just takes A around B by 2 pi. It doesn't know anything about A exchange with A, just taking A around particle A, okay? Sorry? Yes?
So the way you define S here is when, if I understand correctly, is the matrix that diagonalizes n.
Yes.
And then what exactly did you prove?
What did I prove?
Yeah.
So this is just a definition, right? But what this proves is that if I look at this data as the set of, the topological data as a set of braids, okay, I can tell you how many of them there are, okay? Now, this is just a definition of the S matrix. Now, you can actually go further and prove that, the topological spin is also, there's an expression of the S matrix in terms of topological spin. So you can get more topological data than just the S matrix for some theories, not for all of them. So now there's a conjecture that, that if you just have the S and T matrix solutions, those are the same. If you impose unitarity and modularity, those are the same solutions that you'll get. Yeah. No.
The non-trivial statement was that within this formula, nowadays the metrics that diagonalizes. It's the same S that satisfies SO2 zero relations in a fusion controller.
That satisfies the what? I can't prove that it satisfies the modular. I can't prove ST cubed is equal to. Well, I can't prove it because I'm lacking time, But so what you prove in this formula is that if I define this as phases, okay, as like the topological data of my theory. So I just said that if I look at a bulk and think of, just am trying to get, just the amplitudes or the phases that you get by braiding quasi-particles, okay? Now that's that. You can get them from that, okay? And by just solving for that, you know how many of these different sets you have, okay? So that I've proved. I've proved that, so I have a set of fusion rules. Let's just be clear. I have a set of fusion rules. I can know how many S matrices I have, so I can know how many distinct sets of phases I have, okay? You can, of course, prove if, you have 20 more minutes, you can prove that ST cubed is equal to, e to the I 2 pi c over 8 from here. But I can't prove that yet. But what you can prove is that if I define the S matrix as just the set of, phases that you get under braiding, okay, I get distinct theories just from, these fusion rules give me more than one. So this fusion rule has 2 sets of S matrices. This fusion rule has 2 sets of S matrices that are different, okay? Now I said there's 4 theories. Each of those sets of 2 S matrices differ by the topological spin, okay? I'm just trying to get the set of braiding phases, okay? And that I have, okay? Now you might argue that, that's just a definition, the braiding phases, which is true, okay? But I'm just showing you how if you just have fusion rules, you can get, I've showed you how to obtain the fusion rules from microscopics, and then I'm showing you how to obtain the braiding phases or the S matrix from the fusion rules. And well, I can't show that they're the same as that hand-wavy way of getting the phases, but you can use that as an exercise. In any case, so if I look at C equals 2 mod 4, you can just do this and find out that there's two S matrices. They all have 1 on the diagonal, on the first and last row, and they differ by having a plus minus I here and minus plus I here. Okay? And this gives you 2 theories for that fusion. You can just do the S matrix 2 theories for this fusion. And the way, so I told you that there's 4 theories here. Well, the way that is going to come into play is that if I introduce now an exchange matrix, or really let's just talk about topological spin, what happens under rotations of this T4 particle, say, okay? Rotations under the T4 particle squared have to be equal to this number, okay? Plus minus I. So because of this square, you get another 2 possibilities. So that's how you get 4. So I didn't have time to prove you that you get 4, but at least I had time to show you that just in terms of braiding phases, that set of fusion rules has at least 2 theories. It actually has 4 because they differ by exchange, which I haven't been able to introduce yet. So thank you.
Well, thank you.